This question is asking whether we can use a coherent demodulator, that's something like that, to successfully demodulate an AM signal. So a coherent demodulator that's intended for the demodulation of DSB with suppressed carrier, can we also use it to demodulate DSB with a large carrier? Now, what we expect is for DSB large carrier to be demodulated by an envelope detector. So a simple rectifier and capacitor low-pass filter. So that's how we would normally demodulate AM. So the question is, can we use a synchronous, a coherent demodulator to detect and demodulate AM? Now, we can analyze this mathematically, and it's fairly straightforward. If you look at the DSB signal, what does that actually look like? So S, DSB suppressed carrier. What does that look like? That's simply your message signal multiplied by cosine omega CT. And it'll be multiplied by some carrier, so some amplitude, sorry. So this is the signal that we expect to receive here if this was a DSB signal. Now, the question is, can we use it for a DSB large carrier? So to add the carrier term, so if we replace SC with LC, to add the carrier term, all you would do would be to multiply by the modulation index and then add DC. So it would look something like that. So the only thing we've added is that. Now, if we follow the signal as it goes through the demodulator, we should be able to see whether or not it's recoverable. So the first thing we have is a local oscillator. So that local oscillator simply generates a cosine, hopefully of the same frequency, omega CT. So it's the same frequency as the carrier. So after multiplying here, what do we have at that second point? So after the multiplier, we'll simply have the same signal, 1 plus m. I'm going to replace m of t with cosine omega mt. So that's a simple single tone message. So I've replaced m of t, my message, with a single tone cosine. Now I'm multiplying it by cosine omega ct, and then multiplied by cosine omega ct again, because we have this term here. And what I could do is simply say cosine squared. So here we have a cosine from the original DSB signal, and we have a cosine from the local oscillator. Together, that gives you cosine squared. Now, if you remember the identity, cosine squared omega ct can be rewritten as 1 plus cosine 2 omega ct divided by 2. So if we replace that there, that gives us let me keep the brackets, a into 1 plus m cosine omega mt times 1 plus cosine 2 omega ct. Now, if you multiply out, you're going to have, at least 3 terms. You're going to have your DC term, so that's just a over 2. You're going to have this term here. So So let's write that as A over 2 times m times cosine omega m t. And then you're going to have the product of the two cosines. So we can write that as A over 2 cosine omega m t multiplied by cosine 2 omega c t. So when you have a product of two cosines, that gives you two terms, the sum and the difference term. But in either case, whether you have the sum or the difference, because omega c is so much higher than omega m, then all of these are high frequency terms. And these will be removed by the low-pass filter. So if you look at the signal here after the low-pass filter, your message looks like this. And there you can see there are two components. There's a DC component, and here we have our message. So we've been able to recover our message from the AM signal using a synchronous, a coherent demodulator. So these high frequency terms are removed by the low pass filter. This DC term is just a shift. So that simply means that our signal will be shifted. So we have a DC shift of A over 2, but that's harmless. So that doesn't affect the quality of our signal. We can block it using a coupling capacitor if we wanted to, but it's harmless. So our original message is this bit here, and we've been able to recover that. Now notice that our message is actually multiplied by m, our modulation index. So consider two cases. If m is 0, that's 0% modulation, then we still have nothing to recover. So if m is 0, there's no modulation, and even a synchronous demodulator would be unable to recover our message. But what about if m was greater than 1? This is what we call overmodulation. Would we still be able to recover the message? Well, in this expression here, it doesn't really matter what the value of m is. M could be 1, 1.5, 2. It doesn't matter. We can still recover the original message. So even though with overmodulation your message envelope is lost, we can't use an envelope detector, we can still recover the original message using a synchronous detector. So overmodulation, it's not the end of the world if you're using a synchronous detector. So the answer to the question, could a synchronous detector be used to demodulate AM? Yes. If you're asked to justify this answer, you would need to follow the maths all the way through, from the input all the way to the output, showing the expressions at the input and output to each of these blocks.